In this chapter E of the protocol family TCPIP, we will explain typically the transmission control protocol, the TCP protocol. That is one of the most important protocols with IP and UDP and DNS, the most important protocols of the TCPIP protocol suite. The transmission control protocol TCP is was defined in the RFCs 793 and 1323. But in fact, the TCP protocol enables reliable communication between processes, between end-to-end processes. It is guaranteed that the data is transported error-free without loss or duplication in the original order. The protocols of higher layers, such as, for instance, FTP or HTTP, pass data to the TCP for transmission to another process in another end system. The TCP divides this data into segments and pass them to the IP, which divides these segments into datagrams and transports them to the target system. Then here we are the illustration of the different segments. TCP segments is the name of the PDUs of TCP. The protocol data units of TCP are called segments. Then each segment, TCP segment, has a TCP header, and the TCP segment is encapsulated into IP datagrams. It could be encapsulated into IP version 4 datagrams or into IP version 6 datagrams. This illustration shows the division of the data into several segments and the transmission using IP across the network. Then we need to remember to have been clearly learned that TCP provides an end-to-end service. That is end-to-end service. The dialogue, the TCP dialogue, is performed between end systems. And typically, the intermediate systems like routers don't intervene, don't process the TCP segments, only process the IP datagrams. Then that's why the TCP provides an end-to-end service for reliable, connection-oriented, by-stream-oriented, full duplex transmission. That is, the TCP. Remember that the IP networks don't guarantee the correct transmission of the data across the network. There is no guarantee of the transmission until to the end system, nor the, for instance, the order or the error that could happen during the transmission across the network, or the sequence of the messages. But in fact, TCP that runs over IP network will be responsible to guarantee the reliability of the communication. And in order to, for instance, control some aspects as the sequence of the messages, we will see that it's important to establish a connection, a logical connection, in order to reset, to establish the state variables, the params between the the state machines that control, for instance, the sequence of the messages, and that's why we need to establish connections, and that's why this protocol is connection oriented. Another aspect to take into account is that the TCP protocol is byte oriented, is not message oriented. That is, in fact, there is a stream of bytes that are sent from one process to the other process, and in both directions. We will see that, in fact, is a full duplex transmission where there is one end that send data to the other, and in the other way, the other process that transmits data to the other end of the other end system of the TCP connection. And then remember that TCP considers that the lower layers don't offer reliable end-to-end data transmission or transport services. That's why TCP implement several mechanisms. One of them is the error control. The error control, the sequence control, and the congestion control and the flow control. Then remember those are the functions that are implemented by TCP. It's a very complex protocol. In the TCP implement the multiplexing of inter-process communication traffic using the port numbers. Similarly to the multiplexing performed by the UDP protocol. Is byte-oriented full duplex transmission. TCP perform mechanism of segmentation, that is the bytes that need to be transmitted from one end to the other are grouped, are filled what we call the different segments, and those segments are sent across the IP network, encapsulated into IP datagrams. The TCP protocol implement a sequence control in order to guarantee the sequence of data that is received in the end system. In order to implement some other controls like error control and flow and congestion control, the TCP implement a mechanism called automatic repeat on query with a sliding window and go backend mechanism. We will see that mechanism in detail, but remember the ARQ, the automatic repeat on query sliding window, is the mechanism implemented by TCP that perform error control and flow and congestion control. The error control is necessary in order to retransmit some segments that are lost in the in the transmission across the IP network. The flow control is an explicit mechanism that permit to face, for instance, the availability of memory in the receiver buffer side. And the implicit congestion control is a mechanism implemented by TCP in order to avoid or to collaborate in the avoiding of the congestion in the network. Then we will explain one of each those mechanism or functions that are implemented in the TCP protocol. Well, remember the multiplexing of inter-process communication traffic with port numbers. We already explained this in some lectures, in some previous lectures. But in fact, remember that in the connection, the TCP connection is defined by the IP address of each end, the protocol TCP, and the port number at each end. Remember that the address and the port number of each end is defined at the endpoint. Then the connection is defined by the two endpoints and the protocol TCP. Remember also that the port, the server listen generally in a port under 1024. That is a reserved, typically a reserved port, and a privileged port. That is a port that could be used by processes that run with administrative preference or priority in the platform where the process is running. In the side of in the client side, the port used is an ephemeral port, that is a port over 1024. If we need to clarify the concept of byte stream oriented and full duplex of the TCP protocol. TCP is byte stream oriented, full duplex. The data stream is sent in TCP segments. Each TCP segment is encapsulated over IP. The maximum size of TCP segment is given by the maximum payload of an IP datagram, approximately 64 K bytes, that is 2 to 16 bytes minus the IP header, typically 20 bytes. In the event that it is necessary to do fragmentation at the IP level, the TCP segment can be transported by several IP datagrams. And remember, in this case, only the first IP fragment carries the TCP header. This is important to remember when we talk about the different mechanisms of packet filtering in the perimeter control typically implemented in firewalls. This is only a particular case that you need to remember in those scenarios in order to, for instance, implement some security implementations using firewalls, for instance. Transmission, the TCP, then on the target system, the TCP gets its segments back from the IP and checks the error-free transmission. Correct segments, that is the segments that arrives to the target system without errors, are then assembled in the original order. We will see that this is accomplished using the sequence number, passed to the higher protocol, and the reception of the sender side confirmed. Confirmed, that is, the receiver sent to the transmitter a confirmation that is called acknowledgement, and is accomplished using a number called acknowledged number. If a segment is damaged or lost, it is not confirmed, is discarded typically, after which the sender side repeats its transmission. That is, the sender side retransmits the segment that was damaged or lost. The TCP implements flow control between the communication processes in order to avoid the overload of the receiver's buffers. And during communication, the receiving party informs the sender in the confirmation message how much data can be processed in the next transmission in order to establish a flow control and avoid the overflow, excuse me, not the overload, the overflow of the receiver's buffers. Then here we illustrate the segmentation of user data. Then the application send bytes in order to that those bytes arrive in the same order and without errors to the process of the application in the other end system. In order to perform this, there is a buffer. The data is saved in those buffers. In fact, those buffers are FIFO queues. Then those data, that data is divided into segments, to different segments, and each segment is encapsulated in an IP datagram, and that IP datagram is transmitted across the IP network, and in the other end, the IP level bring the data received to the TCP layer level. The TCP software then process the segments and reestablish the order if the order were modified during the transmission. If it's necessary, it will be retransmissions from this end system to the other, and finally, then the information is stored in the receiver buffers, and the application read the data from the receiver buffer. Then remember this architecture of inter-process communication using TCP. Then this is the header of the TCP segment. There are some fields that we already know from UDP, that is the source and the destination port. Remember, the source and destination port are 16 bits long. There are other numbers here, for instance, the sequence number, SN, the sequence number of 32 bits, the acknowledgement number of other 32 bits. There are typically the window size. Remember the window size that is in fact known the advertised window. Then remember the window that is explicitly specified here is what is called the advertising window. That is the window that is advertised by the receiver. Then the window size, remember, is a number of 16 bits. There are typically, TCP header length, because there are options that could be added or not to the TCP header. there are several flags. The most important are SYN, ACK, FIN, and there are others like push, reset, and urgent. But in fact, the most important that we will explain in this lecture is the SYN, the ACK, and the FIN flag. Remember to distinguish the acknowledgement bit and the acknowledgement number. The acknowledgement bit is only one bit that is set, in fact, in any segment, and this flag said that this acknowledged number is significant. In fact, we will see that only the first segment of a TCP connection has the acknowledged number not in 0, but the other segments always have this acknowledgement bit set to 1. Well, finally, there is a checksum. Is a field of 16 bits in order to check the integrity of the segment, not only the header of the segment, but the data, the payload of the segment. Finally, if this bit, urgent bit, is set, here we indicate with the urgent pointer where is the urgent data that is sent. That is a mechanism of transmit data without sequence control. That is what is called out of order data. Well, then remember the source port, the destination port, the sequence number, the acknowledge number, the header length, the urgent flag, the acknowledgement flag, the push flag, the reset flag, the SYN, the synchronous flag, and the finalization flag. We will see all those flags, particularly SYN, FIN, and ACK. The window size, the window size is in fact the slide window for flow control. This number indicates the number of bytes that can be sent before an acknowledgement. In fact, the number of bytes that the receiver could receive starting from the acknowledge number sequence. The checksum, including a pseudo header, we will see the detail of this how this integrity verification is performed using this field called the checksum. The urgent pointer that points to urgent data or out of sequence data, and finally different options. For instance, maximum size payload, that is MS, maximum segment size. Well, then here you are. Typically, the end systems, host 1, host 2. There is in the middle an IP network that interconnect the host 1 with the host 2. Typically, from up to down, we are the access of time. That is, this is the time that that pass. Then, for instance, when we transmit data, typically a segment, the segment is sent at a particular time and arrive to the other end some time later. And once the other side receive the data, perhaps send data in the other way, in the other direction. And in that way, we exchange data between the end systems. But remember, TCP is a full duplex data transmission service. That is, there are two data streams, one in each direction, one from host 1 to host 2, and the other from host 2 to host 1. The control of each stream is independent of the other. Remember this. For instance, we could have, for instance, the data stopped by, for instance, the control flow from host 1 to host 2 because the receiver buffer in host 2 is full. But for instance, in the other direction, the receiver buffer in host 1 is not full. Then we could continue to transmit data from host 2 to host 1, but perhaps we can't transmit data from host 1 to host 2. Then remember this: the control of each stream is independent of the other. Each TCP entity has a transmitter and a receiver. That is, each entity, TCP entity, has two sub-entities, or two sub-entities, one transmitter and one receiver. This transmitter talk with this receiver, and this transmitter talk with this receiver. Each data stream goes from transmitter to receiver. Remember that. Along with the data in one direction, we piggybacked parameters from the opposite flow are sent. Then remember, in a piggyback with the data of the flow from host 2 to host 1, we send the parameters, for instance, of error control, sequence control, etc., that are used by the data flow from host 1 to host 2. Remember that. Those are parameters piggybacked with this data, but that correspond to this data. And those are parameters that are piggybacked into this data, but that correspond to this data. Remember, there is a flow of data from host 1 to host 2 and another independent flow of data from host 2 to host 1. But there is, in fact, with these piggyback parameters, a cooperation between the two flows in order to transmit some control information with the data of each flow. Then, in order to, for instance, establish a sequence control, we need to have, in fact, implement a connection-oriented protocol. The connection-oriented protocol is needed because we need to, for instance, establish the sequence of the data and the error control of that sequenced data exchange. And that's why, in fact, the entities, the TCP entities, are state machines. And we need to synchronize those state machines, exchanging particular information that establish compatible states between the state machines or protocolar machines or automate finite automated. And in order to synchronize those state machines, we need to establish the logical connection. The logical connection then is established exchanging 3 segments. That's why we call this three-way handshake. In the three-way handshake, then before the actual data transfer is initiated, TCP establish a logical computer-to-computer connection between sender and receiver with the so-called three-way handshake. Remember that there are a state machine transmit state machine here, a receive state machine here, a transmit state machine here, and the receive state machine here. But the two pair of state machines are synchronized or established the connection, the logical connection, with only 3 segments. Then, which are those 3 segments? The first one is the segment with the SYN flag set, and the sequence number is equal to what is called the initial sequence number, ISN. This number is chosen by the calling end of the communication, is chosen in aleatory way. Then it is not necessarily a sequence number equal to 0. Typically is any number of 32 bits. But in fact, this segment transport no data. That's why the acknowledgement of this segment point to the sequence number x plus 1, only here, only as if this segment were a segment transporting only one object. After that, and this segment is a SYN segment with the SYN flag set 2. Then a SYN, and host 1 send a SYN, host 2 send a SYN with an ACK. And remember that this first segment don't have the acknowledge flag set, but this one yes, and this is the acknowledge number that in fact confirm the correct reception of the first SYN. And finally, from this end system, we confirm the correct reception of this sequence number of this segment. Remember, this is the numbering of the data from host 1 to host 2. This is the numbering of the data from host 2 to host 1. Then finally, then we establish the connection with this three-way handshake. Once the connection is established, we could exchange data between host 1 and host 2 in both directions. In order to see some details of the connection establishment, remember that the establishment of the logical connection allows synchronizing the state variables of the TCP protocol entities that in fact are state machines or finite automatas. This is the three-way handshake. The initial sequence number is defined. Remember, in the flow from host 1 to host 2, this is the initial sequence number. and in the flow of host 2 to host 1, this is the initial sequence number. And this, in fact, is the acknowledged bit. This is the acknowledged number. We are acknowledging this segment. In this segment, the receiver of host 2 establish a window size, and typically the option specifying the maximum segment size, that is, which is the maximum size of the segment that could be sent by the transmitter of the host 1. And in the last segment, here we are acknowledging this segment, remember, and the receiver of host 1 is indicating to the transmitter of host 2 which is the window size, the window size to use in order to transmit the data from host 2 to host 1. Then remember, the maximum segment size is sent typically in the three-way handshake. And remember that only in the first segment, in this one, the acknowledged bit is not set. And this is important to establish some rules of packet filtering in the routers, for instance, or in the firewalls. When we need to finish to terminate the logical connection, we need 4 segments in order to close the 2 flows. Then one of the 2 hosts would send a segment with the finalization flag set, and then the other end send a segment with the acknowledge indicated. And here we could add, for instance, typically the sequence number of this segment. Then with the acknowledge, we need to establish the acknowledge number in order to indicate that we are confirming the correct reception of this segment. Yeah. In this way, then the flow from the data flow from host 1 to host 2 is closed, but in fact is a half closed. Why? Because perhaps host 2 need to finish to transmit some data from host 2 to host 1. Then host 2 could send the remaining data to transmit. Once the acknowledgements are received, then the host 2 is able to close the flow, the data flow from host 2 to host 1, and then finish with the logical connection, sending simply FIN and receiving an ACK. In that way, we complete or we terminate the connection, the logical connection. Remember that is a full duplex connection. And here you are, typically, typically you are the state machine. And then there are typically several states. Then typically the initial state is the entity is free, is closed, and if we need to establish a connection, we send a scene, and we expect to receive a scene with an ACK, and we receive the scene with an ACK, and finally receive the ACK of we send, in fact, the ACK of this scene received. And finally, we reach the state, the established state. And in the other end, if we are closed and in fact we received, we are listening, for instance, and we receive a scene, in this case we send a scene, in this we receive a scene, and then we need to send another scene, and in fact in this three-way handshake, in this in those states, we need to pass typically from the closed state to the established state. And in order to understand how to pass from the established state to closed, we could exchange different combinations of receiving FIN and sending the ACK. But we could stay in half connections during a while, or typically, if we don't need to send the remaining data, typically we exchange the FIN and the ACK without continue transmitting data. And this is the explanation of each possible state in the state machine, in this state diagram or state machine diagram of the TCP protocol.